Assalamu alaikum. That is lecture 3 of week 3. Course code is CS430. Course title is Microprocessor Programming and Interfacing. So in previous lecture we have covered some subgroups of arithmetic and logic group of instructions. In this lecture we are going to cover the remaining groups of arithmetic and logic group of instructions. So we have to discuss multiplication instructions. There are two types of multiplication instructions. First one is for unsigned numbers, that is MUL, and second type of multiplication instruction is for signed numbers, that is integer multiplication, IMUL. So there will be only one operand, that is mentioned as S, and S may be an 8-bit register or a 16-bit register, or that may be a byte from memory or a word from memory. So if S is of 8-bit, then the multiplication operation will be like that. Multiplicand will be present within AL accumulator of 8-bit AL register, and multiplier will be coming from the S, that is the source operand of 8-bit. So AL is of 8-bit and multiplier is also of 8-bit. So after multiplication, the product will be of 16-bit, that will be stored in AX register. In case of 16-bit multiplier, so S16, that means your multiplier is of 16-bit and your multiplicand is in AX register, that is also of 16-bit. So after multiplication instruction, product will be in DX and AX registers. So that dash sign is for concatenation, but that is not a subtraction sign here. So lower 16-bit of product will be stored in AX register and higher 16-bit of the product will be stored in DX. So your product will be of 32-bit. Now we have to discuss the effect on flags. So only two flags will be affected by mul instruction: carry flag and overflow flag. So if you have multiplied two 8-bit operands, that is multiplicand of 8-bit and multiplier of 8-bit, so your product will be of 16-bit. So there will be two halves of 8-bit in the product. So if the upper half of your result is 0, then carry flag will be 0 in case of mul instruction, or otherwise if your upper half is having some value, some number, non-zero number, then carry flag and overflow flag will be having logic 1. In case of IML instruction, the result which is in AX register of 16-bit, if the upper half is the sign extension of the lower half, that means whatever the sign bit of the lower half, that is copied in the all bits of upper half, then that is the sign extension. So in this case, carry flag and overflow flag both will be having logic 0. But if your sign bit of the lower half is not copied in the all the bits of the upper half, then carry flag and overflow flag will be having logic 1. Now we are going to uh, discuss some examples for multiplication instructions. So here we are having AX is having 0001 hex and BX is having FFFFH. So after mul BX, That will be the result in DX AX registers of 32-bit. AX is having FFFF and DX is having 000. So your result is in the lower half of the 32-bit result. So you may see that DX is 0. That is the upper half of your result. So carry flag and overflow flag both will be having logic 0. And after IMUL instruction, what will be the result? If you see both of these numbers in AX and BX registers as sign numbers, so AX is having a positive sign number, that is +1, and if you see BX register, there is FFFF. If you convert and the MSB of BX is 1, that means that is a negative number, so we have to convert it into 2's complement. So 0001 hex is the 2's complement of FFFFH, so that is -1. In BX you are having -1, so -1 multiplied by +1, you will be having -1 as the result. If you convert -1 in 32-bit hex number, you will be having FFFFFFF. So 8 F's. So lower half is FFFF in AX and upper half of your result is FFFF, that is in DX. So if you see the sign bit of the lower half, that is 1. In AX you are having FFFF and sign bit is 1, and all the bits present within DX are 1. So carry flag and overflow flag both will be having logic 0. So that is example 1. Now example 2. In example 2 we are having AX equivalent to FFFF and in BX register we are having FFFF. So after mul instruction mul BX, the result within AX-DX register will be FFFE will be in DX register and lower half of the result will be in AX, that is 0001 X. Now if you see that the result is having non-zero upper half, that is DX is having a non-zero number, so carry flag and overflow flag both will be having logic 1 after multiplication instruction. Now if you execute IMUL BX instruction, then that will be the result. FFFF means -1 and -1 multiplied by -1, so you will be having a positive one. So your result is 0000 in DX and 0001 in AX. So if you see the sign bit of the lower half, AX is having 0001 and sign bit is 0, and all the bits present within DX are 0. So carry flag and overflow flag both will be having logic 0. Now example 3 for multiplication instruction, we are having in AX 0FFFH, in BX we are having 0FFFH. If you execute mul BX on these values, then that will be the result. DX will be having 00FFH and AX will be having E001 hex. So you may see that the higher half of the result is non-zero. So carry flag and overflow flag both will be having logic 1. After execution of IMUL BX instruction, that will be the result. Both the multiplier and multiplicand are of positive sign. So that the result of mul and IMUL will be the same. So DX is having 00FFH and AX is having E001 hex. So if you see the sign bit of AX, that is 1, but you may see that in DX you are having ones and zeros both. So carry flag and overflow flag both will be having logic 1 here. Now example 4, we are having 100 hex in AX and in BX we are having FFFFH. Now what will be the result of mul BX? So after mul bx, dx will be having 0 0 ffh and ax will be having ff 0 0 h. So carry flag and overflow flag both having 1 because upper half of the result is non-zero. Dx having a result that is non-zero, so carry flag, overflow flag both will be having logic 1. Now after imul bx instruction, if you consider bx value that is negative 1 and you are having 100 in ax, so after multiplication you will be having minus 100. And if you convert minus 100 into 2's complement, so you will be having ff 0 0 hex. So upper half of the result is ff in dx and lower half of the result is ff 0 0 h within ax. If you see the sign bit of ax, that is 1 and all the bits present within dx are 1. So carry flag and overflow flag both will be having logic 0. So that is the operation for multiplication instructions. Now we are having division instructions. So there are two types of divisions. Unsigned number division mnemonic is div. For signed number division mnemonic is IDIV. Both will be having single operand. So that operand may be an 8-bit register or a 16-bit register, or that may be a byte from memory or a word from memory. Now if your S is of 8-bit, that means you have mentioned 8-bit divisor and your dividend will be coming from AX register. So AX will be divided by your mentioned divisor of 8-bit. So 16-bit divided by 8-bit, quotient of this division will be stored in AL and remainder of this division AX divided by 8-bit divisor, remainder will move into AH. On in the second case, if you are having 16-bit divisor, then your dividend will be of 32-bit coming from DX-AX registers. So 32-bit divided by 16-bit, you will be having 16-bit quotient moving into AX register and remainder of this division will be moving into DX register. No flags will be affected after division or IDIV instruction execution. Now here we are having some examples for division and IDIV instructions. So first of all, in first example we are having AX equal to 0020 hex and in CL we are having FFH. So after div CL instruction, that will be the values for quotient and remainder. So division is to be performed between AX and CL. So AX is having 20 and divisor is FF within CL. So after division, quotient will be moving into AL, that is 0, and remainder will be moving into AH, that is 20. As you may see that 20 is lesser than FF. If you see both numbers as unsigned numbers, 20 is lesser than FF. So division is not possible. So you are having quotient 0 and remainder is 20. In example 2, we have considered the same numbers. AX is having 20 hex and CL is having FFH. We have to use IDIV instruction and we have written CL as operand. So divisor is FF and dividend is 0020 hex. Now we have to consider both numbers as signed numbers. So CL is having minus 1 and AX to be divided by minus 1. So quotient will be minus 20 hex, and if you take 2's complement of 20 hex, you will be having E0. So that is the quotient moving into AL, and remainder will be 0 for 20 divided by minus 1. So remainder is 0 0, and that will be moving into AH register. In example 3, we have moved 9000 hex in AX, and CL is having FFH. We have used div CL instruction. So divisor is FF and dividend is coming from AX register, that is 9000. So after division, unsigned number division, quotient will be 90 hex moving into AL register. Remainder will also be 90 hex moving into AH register. Now in example 4, we have moved FFE0 in AX and CL is having FFH. So we have to perform IDIV CL. So FF value present in CL is minus 1 in case of signed number, and AX is also having a negative number. So if you see this number at signed number, that is minus 20 hex. So you have to divide minus 20 hex by minus 1. So you will be having plus 20. So quotient is 20 within AL, and remainder is 0 present in AH after IDIV CL instruction execution. Now we are having some more examples. In example 5, in AX we are having 8000 and CL is having 7F. So after division CL, quotient value will be 102 hex, but that value may not be stored in AL register, so division will not be performed, and dividend value, that is 8000, will remain in AX register. So because quotient value 102 is requiring 9 bit to be stored, but AL is of 8 bit, so quotient may not be stored in the AL register. That's why this division cannot be performed by microprocessor. Now next example, we are having FFE0 in AX and CL is having 20X. We have to perform IDIV CL instruction. So quotient, if you see both of these values as signed numbers, so 20 is a positive sign number in CL as divisor, and dividend is having a negative sign. So we have to convert this into a signed number, that is we have to take 2's complement of this number. You will be having 20 hex. So that is minus 20 within AX as dividend, and CL is having 20, that is divisor. So minus 20 is to be divided by positive 20. So quotient will be minus 1, and if you write minus 1 in hex, that will be FF in 2's complement form, and remainder will be 0 as 20 is divided by 20, so remainder is 0. Now example 7, we are having 810 in AX and CL is having 20X. After div CL instruction, AL will be having 40, that is the quotient value, and AH will be having 10 hex, that is the remainder for this division. Now in example 8, for the same values of dividend and divisor, we have to perform IDIV. So AX is having 810 hex and CL is having 20 hex. IDFCL, as both numbers are of positive sign, dividend is positive, divisor is positive, so there is no change in the value of quotient and remainder. For DIFCL and IDIFCL, both are having same results. So AL is having 40x, AH is having 10h. So in example 1, we were having uh, positive dividend and negative divisor in example 1 and 2, and in example 3 and 4 we were having negative dividend and negative divisor. In example 5 and 6 we were having negative dividend and positive divisor. In example 7 and 8 we are having positive dividend and positive divisor. So we have considered all the combinations of sign for divisor and dividend. Now we are going to start discussing BCD and ASCII arithmetic instructions. Before that discussion, we have to study relationship between different data types. So here we are having a table. In column 1 and 2 of this table, we are having hexadecimal digits and their equivalent binary codes. So hexadecimal digits are from 0 to F, and the equivalent 4-bit binary patterns are given. For 0 hex, you are having 000 binary, and for F hex, you are having 1111 in binary. So these are the binary and hexadecimal digits. Then we are having packed BCD form. If you compare hexadecimal column and packed BCD form column, digits from 0 to 9 are the same, and 9 onward you are having difference. For hexadecimal A in packed BCD form you are having 10, for B you are having 11, for C you are having 12, for D you are having 13, for E you are having 14, and F is equivalent to 15 in BCD form. In packed BCD form, each nibble will be having a digit, but if you see the next column, unpacked BCD form, each byte will be having a digit. So 0 is mentioned as 00 in unpacked BCD form, and 1 of packed BCD form is mentioned as 01, 2 is 02, and until 9 you are having 09 in unpacked BCD form. 10 is written as 0100, so 1 is written in the higher byte and 0 is written in the lower byte of that number. 11 is equivalent to 0101, 12 is equivalent to 0102, 13 is equivalent to 0103, 14 is equivalent to 0104, 15 will be written as 0105 in unpacked BCD form. Now, if you add 30 with unpacked BCD form digits, you will be having the ASCII codes, and these are the entries present in ASCII column. Now, what are the ASCII numbers? ASCII numbers will be used when you are communicating with human beings. Uh, as a programmer, you have to take input from users, and you have to display the result of your calculations on monitor screens. So then you will be using ASCII numbers. So if you are taking input from user, then user will be pressing uh, keys from keyboard. So if user is pressing 5 from keyboard, you will be having the ASCII equivalent of that 5 key, that is 35. So or if user presses 9 from keyboard, you will be having 39 in microprocessor for that 9 key. So these are the ASCII codes, and if you want to display 0 on monitor screen, you have to output the ASCII of 0, that is 30 on monitor screen, to show a 0 on the monitor screen. or if you want to display a 7 on monitor screen, you have to output 37 hex on monitor screen to show 7 on monitor. So that is the purpose of ASCII codes. Now we are going to discuss BCD arithmetic instructions, and these instructions are for pack BCD form BCD numbers. First instruction is DAA, that is decimal adjust for addition. So as we know that microprocessor will be performing its calculation in hexadecimal numbers, but after uh, digits from 0 to 9, there is difference between hexadecimal numbers and BCD numbers. So we have to correct the result present in AL register after calculation is performed by microprocessor to convert the result in PEG-BCD form from hexadecimal. So for that we have to use DAA instruction, and what this DAA instruction will be doing to convert. So that is the operation defined here, that lower nibble of AL will be checked. If that is greater than 9 hex, that means it will be having A, B, C, D, E, F, the alphabetical digits of hexadecimal. Then a 6 is to be added with AL to adjust that nibble. Or otherwise, if the nibble is having digits from 0 to 9, but auxiliary carry flag is 1, then also that operation of adding 6 to the lower nibble will be performed, and as the nibble is adjusted, lower nibble is adjusted, so auxiliary carry flag will be set. uh, for the higher nibble of AL, if higher nibble of AL is having a number greater than 9, that means you are having A, B, C, D, E, F digits in higher nibble of AL, or otherwise carry flag is having 1, logic 1, then a 60 is to be added, 60 hex is to be added with the contents of AL, and carry flag, if you are adjusting the higher nibble of AL, then carry flag will be set after execution of DAA instruction. And these are the flags. Auxiliary carry flag will be changed, carry flag will be changed, parity sign, zero flags will be affected after execution of DAA instruction. And examples are coming in the coming slides. Now second instruction is DAS instruction, decimal adjust for subtraction. So it's also corrects the result after subtraction, and as microprocessor will be performing subtraction in hexadecimal numbers, but after subtracting two numbers, you have to adjust result to convert it into BCD, PEG BCD form. So you are having a result in AL register, that is in hexadecimal, and you have to check that uh, uh, will DAS will be adjusting that number or not. So the operation is given here, that if lower nibble of AL is greater than 9, that means you are having an alphabetical digit of hexadecimal number in the lower nibble of AL, or otherwise auxiliary carry flag is set after the subtraction operation, then adjustment is required, and DS instruction will be subtracting 6 from the contents of AL, and the adjustment is done. Now to show that adjustment is being done by DS instruction, AF flag will be set to 1. Now higher nibble of AL will be checked. If that is having a digit greater than 9, that means there are in higher nibble you are having an alphabetical digit of hexadecimal from A to F, or otherwise carry flag is set after execution of subtraction instruction, Then 60 hex will be subtracted from AL and higher nibble will be adjusted. To show the adjustment, carry flag will be set by microprocessor. And auxiliary carry, carry, parity, sign and zero flags will be affected after execution of the DS instruction. Now we are having some examples for BCD arithmetic instructions, the DS and DAA. So that is first example. Here we are having 68 hex in AL and we have added 23 in AL. So after addition you will be having 8B in AL. So there is no auxiliary carry generated when this addition operation is performed by microprocessor, and carry flag will also be having logic 0 as no carry is generated from the MSB during this calculation. Now if you see the value of AL in the lower nibble, you are having uh, a non-BCD digit, that is B, and 8 is okay. 8 is a BCD digit, but B is not a BCD digit. So that will be adjusted by DAA. So what this DAA instruction will be doing with the contents of AL, it will be adding 6 to the lower nibble and 0 nibble will not be adjusted because it doesn't requiring the adjustment. So 8B plus 06 you will be having 91 in AL register, and as the lower nibble is adjusted, so auxiliary carry flag will be set to 1. In the next example, you have added 68 with 81 hex and result is E9 in AL register, and no auxiliary carry generated, no carry is generated during this addition operation. Now the lower nibble is having 9, that is BCD digit, no, not requiring adjustment, but in higher nibble you are having E, so that is requiring adjustment. So you have to add 60 with E9 when DAA is executed. So 60 will be added with E9 by DAA, and you will be having 49 hex in uh, AL register, and carry flag will be adjusted, will be 1 after execution of DAA to show the adjustment. Now in example 3, you have added 68H with 83H. Now AL is having EB. Both nibbles are having non-BCD digits, so both are requiring adjustment. So now DA will be adding 66 hex with EB to have 51 hex result in AL. And both nibbles are adjusted, so auxiliary carry flag will be set. Carry flag will also be set by DA instruction. Now example number 4. In example number 4, these are the values. AL is having 68 hex and a 29 is to be subtracted from 68 hex. So you will be having 3F in AL. So lower nibble of AL is having and auxiliary carry flag will be 1 after subtraction operation, and carry flag will be 0 after subtraction option operation. Now you may see that AL lower nibble of AL register is having F, that is a non-BCD digit, so that will be requiring adjustment. So when DAS will be executed, it will be adding, we will be subtracting 06 from the AL. So lower nibble will be adjusted. To show the adjustment, auxiliary carry flag will be having 1. In example 5, AL is having 68 and 83 is subtracted from AL. So AL will be having E5 and auxiliary carry flag will be 0 and carry flag will be having 1 as you have taken borrow on the MSB. Now if you see the value of AL, higher nibble is having a non BCD digit, but lower nibble is having 5, that is okay. It is a BCD digit. So DS will be adjusting only the higher nibble of this AL register. So 60 will be subtracted from contents of AL. You will be having 85 hex in AL after execution of DS. And to show the higher nibble adjustment, carry flag will be having logic 1. Example 6, AL is having 68 and 89 hex is subtracted from AL. You will be having DFH in AL register after subtraction operation, and auxiliary carry flag both will be having logic 1, as you have taken borrow on lower nibble as well as on higher nibble. Now DS instruction will be adjusting both nibbles by subtracting 66 from DF. So you will be having 79 hex in AL after execution of DS instruction, and both nibbles are adjusted, so auxiliary carry and carry both flags will be having logic 1. Now some more examples. Example 7. In example 7 you are having 68 hex in AL and you have added 29 hex in AL, so you are having 91 hex in AL register. Here auxiliary carry flag is having 1 and CF carry flag is having logic 0. So AL is having a number, there is no non-BCD digit present, but auxiliary carry flag is having 1. So adjustment will be done by double A instruction. So DA will be adjusting the lower nibble as auxiliary carry flag is 1. So 91 will be added with 06 and you will be having 97 hex as the lower nibble is adjusted. So auxiliary carry flag will be having 1. Next example, AL is having 98 hex and it is added with 81 hex. So result is 19 hex and auxiliary carry flag is 0, carry flag is 1. Now if you see the contents of AL, there is no non-BCD digit present. So it looks like that no adjustment is required, but carry flag is having 1. So adjustment will be done for the higher nibble only. So after DA instruction, AL will during a DA instruction execution, 19 will be added with 60 hex to have the value 79 hex in AL, and carry flag will be adjusted to show that the higher nibble is adjusted. Now in next example, AL is having 98 hex and you have added 89 hex in AL, so AL will be having 21 hex. Apparently this value of AL is not requiring adjustment because of BCD result, but auxiliary carry flag is 1 and carry flag is 1, so both nibbles are requiring adjustment. So DA instruction will be adjusting both nibbles. So 66x is added with the contents of AL, that is 21. So 87 is the result after DA instruction in AL register. As both nibbles are adjusted, so AL and auxiliary carry flag and carry flag both will be having logic 1. Now next example, AL is having 62 and 29 is subtracted from AL. Now you are having 39 in AL. Auxiliary carry flag will be having 1, carry flag will be having 0. Apparently this value of AL is not requiring adjustment because of the BCD result, but because AF is having 1, adjustment will be done by DAS instruction. So after during execution of DAS instruction, 06 will be added with the lower nibble with the contents of AL to adjust the lower nibble of AL. So you will be having 33 hex in AL after execution of DAS instruction. And as the lower nibble is adjusted, so auxiliary carry flag will be having logic 1. In next example, AL is having 28. You have subtracted 93 hex from AL. You are having 95 hex. No BCD digit is present in AL, but auxiliary carry flag is having 0 but carry flag is having 1. So higher nibble is requiring adjustment as carry flag is having 1. So DAS will be adding 6 with the higher nibble, will be subtracting 6 from the higher nibble to adjust this number. So you will be having 35x in AL after execution of DAS instruction, and to show the adjustment of higher nibble, carry flag will be set to 1. That is the last example for DAS instruction. AL is having 22 and 89 hex is subtracted from AL. So you will be having 99 hex in AL. Auxiliary carry as well as carry flag are having 1. So both nibbles are requiring adjustment because of the flags, but the value of AL is having all the BCD digits. But because of the flags, both nibbles are requiring adjustment. So DAS will be adjusting both nibbles by subtracting 6 from the both nibbles. So you will be having 33x in AL after execution of DAS instruction. And to show the adjustment, auxiliary carry and carry both flags will be set to 1. So that is the end of the current lecture.